to the stream on functions. Let me set up the chat room so that we can have a nice chat throughout the stream. And today we're gonna look at functions. Now, functions are not necessarily the newest idea that we have learned in our math journey up to our undergrad years. However, to phrase it in a mathematically rigorous manner might take a little bit of effort compared to what we have learned prior in high school. We're gonna take whatever we know in high school and generalize it and put it on a little bit more rigorous formulation and definitions. So let's start off with the first question, and that is this question over here. We'll fix two sets A, B as a subset of the integers, and we want to define the relation from A to B in the following manner. We're gonna consider points x, y inside A cross B with the property that y equals to x squared minus 1. And at this moment, we might be thinking, wait a minute, isn't this just a parabola? Isn't this a function that we're all relatively familiar with? This is where we need to take a step back and look carefully at what we mean by a function. So let's define this relation. And now we are gonna consider this following setup. Suppose A is the collection of integers from -2 to 2, and B is the collection of integers from 0 to 3. The question is this relation a function? And before we can answer the question, the first and most important part of the problem solving process is to even figure out what the problem is in the first place. What do we mean by a function? So prior in high school, we might have learned that functions are formulas, roughly speaking, that take in an input and spit out, output and output. And for every input, we get exactly one output. So that is precisely the definition of functions, but now we're going to formulate it a little bit more properly in the context of relations. So let's first define what we mean by a function. We will let R be a relation from A to B. A relation is a subset of points of connections from A to B, and a function is a special type of a relation. We say R, and usually for functions we like to use the notation f because f for functions. So let's use that. Let f be the relation from A to B. We say that f is a function precisely when it satisfies two important properties. We'll call them f1 and f2 respectively. So what's the first property? Let's very quickly visualize the situation on the top right corner over here. So we want to communicate the idea of a function. How do we communicate the idea of a function? Roughly speaking, for a function, every input must have at least one output. I think that makes sense. If I take in something, I need to give out something, and I need to give out at least one thing. So that's the first requirement for the relation to be a function. We'll need to look at the second requirement in just a moment. So first requirement is that for any input into the relation, you can think of A as the quote-unquote input set, we call it the domain. There exists an output Y in what we call the codomain with the property that X is connected to Y. In other words, when I take in X, I will at least release output Y, minimally. And in general, a particular point could have be a particular point could be connected to two other points. It's entirely possible. But a function is really, really restrictive. A function tells us that, or rather, a function, what we would like a function to behave is that if it takes in one input, it releases at least one output, and at the same time, at most one output as well. So how do we communicate the idea of at most one output? Here's how we do it. So for any inputs, A, and for any outputs, y1, y2 in B, if in some weird way we encounter the situation where x is connected to y1 and x is connected to y2, in this rather awkward situation, a function is really restrictive. A function will tell us that, no, the y1 and the y2s, they look different in the hypothesis, but in reality, they must be one and the same. They must be one and the same. And that's the idea. So f1 tells us that every function has at least one input. I like to think of it this way. Every function has at least one output. Every input has at least one output. And the second condition tells us that every input has at most one output. So that's the formal definition of a function. We can use this to answer our question. Is RAB a function? Let's make some space. So is RAB a function? Well, what exactly is RAB? RAB is going to be all of the points that satisfies this particular equation. RAB is going to be all of the points. You take the x's from A, you take the y's from B, you connect the points whenever they satisfy this particular equation. So, how do we make sense of RAB? Let's check. Suppose x equals to -2, then y has to be equal to -2 squared minus 1, that's 3. In fact, we can do a small table over here. This is relatively informal, but it sort of conveys the idea. -2, -1, 0, 1, 2. If we substitute x equals to -2, we'll get -2 squared minus 1. That gives us +3. If we substitute -1 into the equation, we'll get -1 squared minus 1, so that's 0. And likewise, if you sub in x equals to 1 and x equals to 2, you're going to get 0 and 3 respectively. But that leaves us with the 0, and when you substitute x equals to 0, you will get y equals to -1. What does that mean? That tells us that RAB can only be the collection of points -2, 3, -1, 0, 1, 0, and 2, 3. But wait a minute, don't we have a 0, -1 here? The problem is that B does not contain -1. So this is not one of those points inside this particular relation. And what can we conclude therefore? We can conclude that, wait a minute, the input 0 does not have an output inside this relation. Let's make a little bit more space. The number 0, the input 0, does not have an output because its output is -1, but that should lie in B, but it doesn't lie in B. So let's see. Choose x equals to 0, which lies inside A. For any y in B, xy does not lie inside the relation. Therefore, we have found a particular item such that no matter which, or rather let's put it this way, we found a particular input such that for any output in B, this guy gets violated. But that means we have violated F1. Therefore, F1 is violated. Since we have shown that the negation of F1 is true, F1 itself must be false, and that tells us that RAB is not even a function to begin with. So RAB is not even a function. Now we can tweak this example just a little bit, and we will be able to get a function. How should we tweak this? Let's consider instead B prime to be the collection of outputs including -1. Now, with B prime in the picture, we know that RAB prime is going to be everything in RAB, but now including the pair 0, 0, -1. And once you include this pair, you can now show that F1 and F2 are satisfied, which means that RAB prime is a function. Right? It is a function because for every input we have at least one output. We can slowly check. And each input has at most one output. For example, the number -2, the input -2, has only one output, 3. Because there is no other pair of the form -2 something. The only pair we have here is -2, 3. So that's that, and we can show that R of A, or rather R sub A comma B prime is a function. Let's clean up the board and look at our next question. Here's our next question. We now want to find a set B that lies inside the integers from -4 to +4. Such that R sub AB is a surjection. And before we even continue with the question, the first thing to ask is, what do we mean by a surjection? The first thing to define is a surjection. So let's properly define a surjection over here. A surjection, first and foremost, is a function. So here's how we're going to write it. A function f is a surjection if it satisfies a particular property. Now, what property are we looking at over here? There was a property for functions earlier on where every input has at least one output. Surjections are basically a flip version of that statement, which is every output has at least one input. So here's the technical formulation of a surjection. For any output, there exists an input with the property that y equals to the output of that input under the function f. So firstly, f is a function, and once we have a function, we can use this notation. This notation is another way, or rather a more user-friendly way of writing x, y in f, which makes sense after we've established that there is no ambiguity in this expression. And so, a function is a surjection if every output has at least one input that points to it. That's it. So that raises a question. We want to find B such that RAB is a surjection. Now the first thing to note is that it must be at least a function. In other words, every input must have at least one output and at most one output. So minimally, RAB has to include the following points. For the input -2, we must have the output 3. In fact, we basically need all of the items in the table over there. That tells us that we have the input and the output. We need that particular pair inside the relation in order for it to be a function in the first place. Not even a relation, just a function. Well, not even a surjection, just a function. But this relation is only legit if A is equal to the set as follows. And what about B? B has to be a set that makes this at least a function. So let's first look at all of the different outputs that we are getting. We are getting 3, we're getting 0, we're getting -1, we're getting 0, and we're getting 3. So we can put in 3, 0, and -1 into B. And we can check that B, as we have defined here, is indeed a subset of the integers from -4 all the way to +4. But that raises the question, okay, fine, we now have a function. But is this a surjection? We need to check that every input gives us at least one output. Scratch that. We need to check that for every output, we can find at least one input that goes to that output. So let's see. For the output 3, do we have an input that points to 3? Well, yes, because for 3, we have -2, and -2 does lie inside A. So we're good to go. In fact, this is the point over here. Now, we have actually two inputs, right? We actually have -2 as an input for 3. We also have 2 as an input for 3. Does this violate any functions definition? Hi Isaac, hi Elon Musk, thanks for tuning in. You got a $1,000 for me. So there could have been 2 inputs, but it doesn't matter because the function definition says that for any input we have at least one output and at least one output and at most one output. Here the condition is nothing to do about the inputs. It's about for every output we can find at least one input. So we're good to go. It still works. So for 0, we have the input -1. We also have the input 1, strictly speaking, so that works. And for -1, we have the input 0. And this tells us that for every output, we can find at least one input that connects to the output. Therefore, this is not just a function, this is also a surjective function. And we are good to go. Let's clean up the screen and look at our next question. For our next question, we are interested in asking about sort of a reverse question. So we'll suppose that B is the collection of outputs 0, 1, 2, and 3. And we want to find a subset of the inputs from -4 to 4 with the property that RAB is an injection. And even before answering the question, the first thing that we should ask ourselves is, well, what's an injection? Is it just the injection we go to the clinic in order to get any booster jabs and whatnot? Well, at least in the context of functions, here's how we define an injection. If surjections is sort of the flip version of F1, which is saying that every output has at least one input, then injections is the flip version of F2. In other words, every output has at most one input. And we can formalize it this way as follows. A function f is an injection if for any output, right, and we can represent outputs as f of the inputs. So we can say that for any two inputs, if the outputs are the same, then we can only have one conclusion. We only can get the inputs being the same as well. Injections tell us that for every output, there is at most one input. In other words, if you have two outputs that happen to have the same value, the inputs that produce the output can only be one and only one. Well, at most one, but you get the point. Well, one and only one actually, but that's fine. So we need to find an example of A such that RAB is an injection. So let's figure this out. We need to consider our inputs. So our inputs are going to be these guys, right? So let's consider, let's just use the easiest one, x equals to 0. So, well, we can't do that. X equals 0, then the output is -1, but B doesn't contain -1, so we can't use 0. We can use 1, right? Because if we plug in 1, 0 is an output in B. So let's consider RAB to be equal to the set of connections from 1 to 0, where A is the set containing 1, and B is in fact the set containing 0, 1, 2, 3. We can check that this is a function because for any input, there is an output, right? The output 0 does lie inside B, and we are good to go. The question asks if we can get an injection. Right, so this is our proposed answer. The question asks if we can get an injection. Well, I think we do have an injection here, right? Because suppose we have any two outputs, or rather we have any two inputs. That's the only input, right? And the outputs are the same, then the input must be the same. Let's just put it this way. Suppose x1, x2 are in A with the property that RAB x1 equals to RAB x2. there's only one possible value that x1 and x2 can take, right? It's only 1. That's the only value that it can take. So that's kind of awkward. But that is the answer. That is actually our answer. And therefore, the choice of A being just the set containing 1 allows our AB to be an injection. Because every output, in this case 0, has at most one input. That is 1. So it's possible. Yes, it looks kind of strange. It's not the usual curves that we might be familiar with in high school. Nevertheless, it's still legitimate according to our definitions of a function, of a surjection, as well as an injection. It's completely legitimate. Okay, let's move on to our next question and explore surjections and injections a little bit more. Now afterwards, we're gonna go and look at how to prove that some functions are surjections and whatnot, and then we might dip our toes in some slightly more higher order questions, if you would. So let's recall the definition of a surjection. We say that f, the function f from a to b, is surjective precisely when, for any output, there exists an input that gives the output. The questions are taken from tutorial 7 of the CS1231 tutorial notes. And I am going in a slightly different sequence from the notes to sort of introduce the different concepts along the way. Nevertheless, I'm gonna just flash all of the questions on the screen so you can just sit back and enjoy the show if you would. And it's still gonna be fine. So here's the question. This is the function from a to b. It is a surjection precisely when, for any output, you can find an input that produces the output. Alright, so that's what it means. For every output, you can find an input that produces the output. And we want to ask which of the following conditions are equivalent to surjectivity. Let's just look at what are the conditions we're talking about. So here's the first condition. The first condition states that for any x in A, for any input, there exists y in B with the property that y equals to f of x. So the question is asking us, okay, here is the formulation of surjection. The question is it true that these two guys are equivalent? Is this formulation, is this proposition equivalent to the formulation of surjection? And the most useful thing we can try to attempt is to actually rephrase the question using symbols and see how the symbols differ from one another. So in this case, we are thinking about for any x in A, aka for any input, right? So this is for any input. There exists y in B, aka there exists an output, with the property that y equals to f of x. So we want to check if this proposition is the same as this proposition. And we notice there's a little bit of a swap in terms of some of the symbols. And that should be an indicator that we're probably not going to get equivalence here. Pretty unlikely. And how do we check that this is the case? Well, let's find a function that violates one of the conditions. Equivalence means that they're always true at the same time or always false at the same time. But non-equivalence means one is true and yet the other is false. Then they don't have the same true values, you don't get equivalence. So let's define a function, and let's define our function in this manner. We've got the function A. We're going to define it as 0, 1. And we've got a function B, which is the function, well, sorry, give me a moment. A will be AB, B will be 0, 1. You could use any symbols you want as long as you have multiple items. And let's define the function in this manner. Let's define a function like this. Let's throw A to 0, and let's throw B to 0 as well. And let's check. Let's see if the conditions are satisfied in one instance and yet violated in another instance. So let's take a look. We call this function f. Let's check. For any x in A, is there a y in B such that x points to y? Right? There's an arrow from x to y. Well, for the input A, we can find an output B such that A points to 0. And for the input B, we can find an output 0 such that B points to 0. That's totally legitimate. So in fact, under this particular formulation of this particular function, A is true. Under this particular formulation, it is true. However, let's check for star. Let's see whether the formulation for star is a legitimate formulation. Let's take a look. For any y in B, can you always find an x such that x points to y? Well, what about the guy 1? What about the output 1? There's an output 1 in B, and yet no one in A wants to be his friend, right? Nobody in A is pointing to 1. Which means that star over here is false. And if it's false, it means that one statement is true and yet the other statement is false. That tells us that these two statements are not equivalent. So conclusion. A and star are not equivalent. We were checking and we were asking whether the equivalence holds, and the conclusion is that these two statements are not equivalent at all. We have a few more statements to check, so let's get used to it and rewrite the quantifiers. Is a good way to revise our quantifiers as well. It's a good way to recap on those ideas. So for part B, we have this statement. It says sum y in B is equal to f of x for all, or well, for some x in A. So this is the statement in B. We once again want to ask the question, is B equivalent to star? That's the question. So let's take a look, and well, let's first translate B before we try to answer the question. So it says sum B is equivalent to f of x for sum A. We can rewrite that as sum y in B is, there exists some y in B with the property that there is some x in A with the property that x points to y. Let's write that out properly. So we can write this as sum y in B has a property that there is some x in A with the property that y equals to f of x. There is some guy in B such that there is some guy in A such that y equals to f of x. And that's the question. Is that true or not? Well, just like before, let's take a look. Is it true that there is some output that such that there is some input that points to that output? Well, the answer is yes. Here, you have the output 0, and you have the output A, and A points to 0. We didn't even need B pointing to 0 in this context, but you know, it is what it is. Well, we do need it if it's required to be a function, but no worries. So, this statement is true, right? This guy is actually true, B is actually true, and yet we still have seen that the star in this function, we've seen just now, is false. This one guy, number 1, does not have an input that points to 1, right? Surjection tells us that every output must have at least one input. However, here we have one input such that there is no, here we have one output such that there is no input. And basically, star is still false, and therefore, are they equivalent? We have found a situation where B is true and the star is false, which means that they are not equivalent. Therefore, B and star are not equivalent. Doesn't work, unfortunately. We're gonna clean up the board and look at the remaining 2 statements which we want to check whether they are equivalent to surjection or not. And by cleaning up the board, I mean copying and pasting and creating the new questions in the new page so that I can reduce the amount of effort I need to rewrite everything. So, part C is a little bit tricky, but this is what it says. All f of x's, where x is in A, are equal to the same y in B. This is the proposition in C, and we want to check that C and star are equivalent, but we do have a question. In the question, we are asked to give a function f from A to B to 0 to 1. So in other words, if the equivalence is true, we need to prove that it's true for any function we wish. If the equivalence is false, we just need to create a function with input set AB and output set 0, 1. And that's precisely the function that we are considering in this situation. And here's the function that I've been using for part A and B as well. In part A, we have shown that the statement in A is not equivalent to the start statement. Let's take a look. So here's the statement in A, and we can rewrite this in symbols. We wanted to check whether this guy is equivalent to this guy, and in this case we have a suspicion that is not actually equivalent. That's why we can use the function diagram over here. We can create a function from AB to 0, 1 and show that, hey, this actually violates this condition. Well, it violates in the sense that one side is true and the other side is false. So that's what we mean by that. We'll look at another question later on injectivity as well, so stay tuned for that. So let's recall the question let's look at the question for part C. We want to ask whether C is equivalent to star. And C says that all fx's, where x is in A, are equal to the same y in B. And this takes a little bit of parsing, but what do we mean by this? We write here, or rather in this sentence, it says that all f of x's for any x in A, all these fx's are equivalent, or not equivalent, they are equal to the same y in B. So it's not just equal to some y in B, but it is equal to one particular y in B. In other words, all the fx's will point to this singular B. Or rather, point to this singular y in B. That's the idea over here. So if that's the case, sort of the y in B sort of controls all the x's. And we can phrase it this way. There exists a y in B with the property that no matter which x you choose from A, fy must equal to f of x. here the key element, or rather the key phrasing, is the fact that it's all pointing to one particular y in B. The x's, each x, is not like x can find its own, one x can find its own B and another x can find, or rather, one x can find its own y and another x can find its other y. No, they're all pointing to the exact same y. That's the phrasing in this question. And we will get the quantifying, well, we quantify it as there is a y in B with the property that for any x in A, y will equal to f of x. And once again, let's look at the statement over here and compare it with the statement in star. As we can see, it looks almost the same, except that the quantifiers are swapped. And this again suggests to us that this statement is probably not equivalent to star. Now, we have a hunch. We still have to prove the hunch. And rather comically, we're going to use the exact same function to prove that C is true in this context, because there is an element y, it's called 0, such that no matter which guy you put, no matter which input you choose, it's gonna point to 0. So it's kind of weird. It's like, wait a minute, this function has been serving our purposes for everything else. It happens. It can happen. And, well, at least for this particular proposition, there is a y such that no matter which input you consider from A, it will point to 0. That tells us that C is true once again. And yet, by the very same function, this function actually causes the star to be false. It's kind of ironic, but it is what it is, and therefore C is, or rather C and star are not equivalent. Now there's a part A, part B, part C, and there's a part D. So you might be thinking part D is probably not equivalent also. Or you might be thinking, we've seen 3 instances where it's not equivalent. We probably will get an instance when it's equivalent. In either case, let's just take a look at the question. Here's part D. And part D says this. No y in B is different from all the f of x's where x is in A. And it's really hard to work with no blah 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 blah. It's a really difficult thing to do. In general, it's really confusing. So I'm gonna read this question as the negation of there is a y in B that's different from all x in A's. And what that means is that is the negation of there exists some y in B with the property that no matter which x in A you choose, y is not equal to f of x. So it's the negation of some y in B is different from any fx. What that means is that it's the negation of there is some y in B with the property that no matter which input you choose, y cannot equal to f of that input. And once you have a negation symbol in there, pretty much my life's the life's mission of simplifying everything is to try to get rid of the negation symbol. And let's just see whether we get something similar to star or not. At this point in time, we're not actually trying to solve the problem, we're actually just trying to simplify it so it's easy enough to make sense of the question. But what that means is that we can push in the negation symbol and all of the quantifiers will get flipped. If you want a review on that, you can go check out my videos and streams on predicate logic in some other parts of the channel. So we can write this proposition as the negation of there exists means for all. The negation of for all is going to be there exists. And the negation of not equals is the negation of equals. So it's y equals to f of x. And surprise, surprise, turns out that this guy, D, is in fact equivalent to star. So finally, we get a situation where the two propositions are indeed equivalent to one another after 3 other questions with the exact same counterexample. Now you might notice that this counterexample is really, really useful. We'll probably use it again in the next part. We've explored a bit of surjectivity this time around, but now we can go and explore injectivity. So let's take a look at injectivity and see what we can get from injectivity. Once again, we'll let f be a function from a to b. And we say that it's injective when every output has at most one input. So we can phrase it this way. For any inputs x1, x2 with the property that they share the same output, there's only one possibility. They must share the same input. And there could be a few ways to phrase this, but let's just work with this definition for the rest of discrete math. And in practice, in any part of math, you probably will use this. This is pretty much the most useful one among all the different formulations. So let's take a look at part A. Part A will ask this question. For all x1, x2 in A, whenever x1 equals to x2, we have f of x1 equals to f of x2. And once again, the question is asking whether A, we'll call this a dagger. We're asking whether A is equivalent to dagger. That's the question, right? If it's true, we need to prove it. If it's not true, then we need to provide a counterexample. I think the right way to phrase it is A equivalent to dagger. I think this is the correct notation. Alright, so let's first parse A. A looks rather straightforward because it tells us that for any x1 and x2 in A, under the condition that x1 equals x2, then f of x1 equals to f of x2. So we can compare the propositions in dagger and A, and we can see that the difference in the proposition here is the fact that the expressions are swapped, right? Here we have a situation of P implies Q, and here we have a situation of Q implies P. So usually, when we try to reverse the argument, usually it doesn't work. There are special cases when it does, but in general, it's not going to work. And we suspect it's not going to work, we still have to prove it. And surprise, surprise, we're going to use the exact same function that we have defined in question 2. But that being said, we're going to redraw the function here. So here's A, here's B, here's AB, here's 0, 1. We're going to point A to 0 and B to 0 once again. Let's check that the definition is satisfied. Let's see. If x1 equals x2, in other words, if we get one particular input, then the outputs must be the same. Well, the output must be the same. Exactly, that's it. Right? So every input has exactly one output. Every input has exactly one output. And the statement in A is true. Or rather, for this particular function, this proposition is true. However, for the dagger, have we violated this condition? Well, the dagger says that if the output is the same, the inputs must be the same. But this function over here gives us a situation where you have an output with, well, two inputs. So the dagger is false. And since you have a situation of the left side being true and the right side being false, you can conclude that A is not equivalent to dagger. So it's kind of weird that one function could really just destroy the argument throughout different ways we flip the quantifiers and all the negative signs and whatever. It's kind of surprising. So let's look at the next one. And I'm gonna leave the diagram there because there's a high chance we're gonna probably use it again. Now for all, B says that for all x1, x2 in A, whenever x1 is not equals to x2, we have f of x1 is not equals to f of x2. So the phrasing is really similar, and we can basically use the exact same formulation. Except now, instead of x1 equals to x2, is x1 not equals to x2. And similarly, it will be f of x1 not equals to f of x2. Informally, this tells us that different inputs must give us different outputs. So once again, we can compare this expression with this expression, and once again we see that we are getting a flipped version. The expression over here is of the form P implies Q, and the expression over here is, well, not Q implies not P. But I think we have a result. We call this the contrapositive, right? The contrapositive of P implies Q is not Q implies not P. And it turns out that the contrapositive is equivalent to the original conditional. Right? It's actually equivalent because, let's recall that very quickly, that P implies Q is equivalent to not Q implies not P. A conditional is equivalent to its contrapositive. That's always going to be the case. But if that's the situation, then I think this is basically the same thing as dagger. And that tells us that, well, we do get B and dagger being equivalent to one another. These two are equivalent. Surprise, surprise, it is equivalent, right? So therefore, B is equivalent to dagger. That's really surprising as far as I'm concerned. I'm like, oh, I expected it to be false, right? Like genuinely, just as I attempt the question. But it happens. So let's clean up the screen and look at the next few questions. Let's look at the question over here now. Well, I forgot to clean up the screen. I've just rearranged everything. Let me clean up the screen. Now let's look at this question. This says this way. There are no elements x1, x2 in A such that x1 is not equals to x2 and f of x1 is equal to f of x2. And once again, we are looking at the question of whether this proposition is equivalent to dagger or not. Question. Are they equivalent? Now, once again, it's really hard to work with there are no elements. So I like to think of there are no elements as the negation of there are some elements. And then hopefully we can do some logical manipulations so that we will get a simplified proposition. So it's the negation of there are some elements x1 and x2 with the property that x1 not equals to x2 and f of x1 equals to f of x2. So that's how I would think about this situation over here. And let's try to simplify this and hope for the best and see what we get. So the negation of there exists is for all. And we're negating a conjunction, so we're going to write the negation of the conjunction. Whoops. The negating of the conjunction. And this looks kind of annoying, but we can push in the negation symbol using De Morgan's laws so that the propositions get flipped and the and gets flipped to an or. So this is the proposition, and this proposition looks a little bit sussy. Looks a little bit like this guy. Right? Takes a bit of effort, but if we think about it, turns out that these two things are actually the same. Let's write it this way. C is equivalent to this. Now dagger is equivalent to this guy. But this tells us that we can write negation as implication. What was I saying? We can write implication as a disjunction, right? So we can write P implies Q as negation of P or Q. And sometimes from right to left is a bit difficult, so I like to just simplify the implication, make things a bit clearer. So we can write P implies Q, and we can verify using truth tables, as negation of P or Q. So we can write this as negation of P or Q. And it turns out, wait a minute, this guy is the same, this guy is the same, and we can conclude that they are equivalent because disjunctions are commutative. Well, disjunction is commutative. So we've shown that C is equivalent to all of these guys, which is equivalent to dagger. And surprise, surprise, turns out that the answer over here is true. I expected it to be false. I have to be honest, I expected it to be false, but I'm hoping the next one's false because I want to use that same function to resolve everything. So let's look at part D. And part D says this. There are distinct x1, x2 in A that make f of x1 equals to f of x2. Once again, we want to check whether these two things are equivalent or not. We can once again write it out using symbols. So this tells us that there exists x1, x2 in A that are distinct. Firstly, there exist these two guys, and secondly, they are distinct. So in other words, we do claim that there are distinct guys. So there exists x1 and x2 in A with the property that x1 and x2 are not equal to each other, and at the same time, they do make f of x1 equals to f of x2. Now this is a really bold claim. It's telling me that, well, I can find two distinct guys such that f of x1 equals to f of x2. It's almost like a direct violation against injection, right? Because injection says every output has at most one input. Here I am just literally violating the condition, which is there is an output with at least two inputs. So we could use the same we could use a counterexample. So let's use this counterexample. Here's A, here's B, here are the inputs, here's the outputs. And we can point A to 0 and B to 0. And that would allow us to have a situation where there are distinct x1s and x2s such that they have the same output even though the inputs are different, and the definition of injectivity will be violated in this situation because there is an input with there is an output with at least two inputs. But I want to strengthen the argument a little bit. I'm going to be an even more bold than just a counterexample. Right? Sometimes, most of the times, we stop at counterexamples, but here I want to go a little bit further. I'm very angry. It's directly violating injectivity. So let's look at this claim. So here's my claim. Let's rewrite dagger as for any x1, x2 in A, if the outputs are the same, then the inputs are the same. So here's the claim. Not only is D not equivalent to dagger, but D is equivalent to the negation of dagger. That's my claim. And here's how we're going to prove the claim. Let's negate dagger. So we negate this guy. We will negate this guy. And we can push in the negation symbol as usual. Negations will flip the for alls. So we get there exists. And we are negating an implication. Right? We're negating the implication. How do we negate implications? To negate implications, we recall that the negation of P implies Q is actually P and not Q. So we're going to apply that result. In this case, P is fx1 equals fx2. And x1, the negation of x1 equals x2 is x1 not equals to x2. And by commutativity, we actually do get the same things. Right, so it's really, it's not just like the other counterexamples where it's not true in general, but sometimes it may or may not be true. Here's a really strict one. D is the direct contradiction, the direct negation of dagger. If dagger is true, D must be false. If D is false, dagger must be... Well, if D is true, then dagger must be false. It's the direct negation over here. It's a really strong connection this time around. So that sort of helps us appreciate the different ways to formulate injections. Some work, others don't, and usually every output has at most one input. That's good enough for practical purposes. So we're going to look at a question next, which helps us get used to the definitions of functions, surjections, and injections in our proofs. Let's consider this relation. It's defined this way. Let's not worry too much about what it means. We'll try to interpret that later. And we are viewing this as a relation from Z to Z, from the integers to the integers. what that tells us is, okay, how do we go on from here? Our first claim is that f is a function. So just by looking at this particular formulation directly, it is not entirely obvious whether or not f is a function. It's just not obvious. How am I supposed to tell if f is a function? It's not obvious. So we're claiming that this guy is a function, and what this looks like is that for the input n, you can find an x such that at least one of these two things are satisfied. And I think the idea here looks very similar to something we might be familiar with. Here, either n is equal to 2 times some integer, or n is equal to 2 times that integer plus 1. These are the formulations of an even and odd integer respectively. So we could try to go ahead to use that to our advantage. Now let's prove that f is indeed a function, and to prove that it's a function, we need to verify two conditions, f1 and f2, even though f1 just ended. So that's that. Let's first check f1. Our goal is to first check f1, and then we'll check f2, and then we'll be good to go. So the first thing to do is to recap the definition of f1. So let's try to recall the definition. f1 tells us that every input has at least one output. So proof, our goal is to show that for any input, in this case the input will be n. By the way, let's all switch the x's to y's, because my brain registers x as an input, right? But let's replace this with y's, because y is an output in general, right? We use y to represent output. So let's use y rather than x. It's really confusing. So for any n in Z, our goal is to show that there exists a y in Z with the property that either n equals to 2y or n equals to 2y plus 1. So let's go ahead. Let's fix our input n, and now we are on a hunt to find an integer y. Now, n being an integer, we have a result, or rather it kind of makes sense that n has to be either even or odd. Now I can quickly prove that later, but roughly speaking, we can use the fact that n is either even or odd. So then n is even or odd. It's one of these two things, right? It's either even or odd. And if it's even or odd, then we will get slightly different expressions. Now if it's even, then you can find an integer y such that n equals to 2y, because that's what it means for n to be an integer, an even integer. Right? But isn't that precisely the proposition we were trying to prove? Right? That's precisely what we're trying to show. We're trying to show that this guy is true. On the other hand, if n is odd, then you can find an integer y with the property that n equals to 2y plus 1. That is by definition what it means for n to be an odd integer. And it turns out that that's precisely the answer over there, right? That is that. Now after we're done with this question, I'll quickly give a proof that establishes that any integers must be either even or odd. It's sort of a simple result, but let's just prove it anyway. But we'll do that later on. So we've shown, right? We've fixed any input, and whether n is even or odd, we can find an output that satisfies this condition, which means that f1 is satisfied. Now let's clean the board and go ahead to solve for f2. we've shown that f satisfies f1. Now let's show it satisfies f2. And f2 says that for any input, you can have at most one output. So let's phrase that properly. Our goal is to show that for any input, if we have two outputs, the output must be the same. So let's phrase it properly. And for any integers y1, y2 in Z, suppose n f1, well, n y1 I mean, lie inside f, and n y2 lies inside f. If these happen, you must get y1 equals to y2. That must happen. In other words, you can only get at most one output. So let's go ahead. We'll fix n as an integer. And let's fix our possible outputs as well. And we're trying to prove an implication. I believe the implication looks a bit like this. There we go. So we need to start by assuming that the hypothesis works. Let's suppose this works. Now, once we have this expression, it's not exactly obvious what we can do with it. We might need to unpack the definition. And for ny to be inside the function, it must satisfy this condition. So unpacking the first condition here means that, let's do it this way. This means that you can unpack the first condition, and at the same time you can unpack the second condition. So the first condition writes as n equals to 2y1 or n equals to 2y1 plus 1. And the second condition reads as n equals to 2y2 or n equals to 2y2 plus 1. Let's use the logical notation here, because now we notice there are some ORs that we can handle. So we can distribute the ORs, aka our rainbow method. We can open up everything, and we're gonna get this situation. I need a little bit more space. This is sort of annoying, but it is what it is. It's just kind of annoying, but it is what it is. So let me try to rearrange this. That looks nice. So we've unpacked this hypothesis to be a disjunction of 4 different situations. How are we supposed to make sense of these situations? Let's just see what each situation gets us. Right, our goal is to eventually show that y1 equals to y2. So let's take a look and see what happens. Let's call this first situation 1. We'll call this 2. We'll call this 3. We'll call this 4. And let's unpack each of these situations. Let's unpack 1. And, well, 1 means that n equals to 2y plus 1, and at the same time, n equals to 2y2. So, well, the ends are the same, right? So we're gonna get 2y1 equals to 2y2, which means that y1 equals to y2. And it turns out, I'm pretty sure about this, 4 also gets us to that situation, right? 4 also gets us to 2y1 plus 1 equals to 2y2 plus 1, which means that with enough algebra, y1 equals to y2. But what about situation 2 and situation 3? That's kind of annoying. So what happens in these two situations? In situation 2, we're getting 2y1 equals to 2y2 plus 1, which tells us an even number on the left is equal to an odd number on the right. But that's a contradiction, right? You can't have a number that's both even and odd at the same time. We're going to prove that in a moment, so stick around if you are interested for that, which is a contradiction. You're going to get false. You might be wondering, wait a minute, does this sort of violate whatever we're trying to establish? Don't worry about it. We're going to see what happens in just a moment. Now similarly, 2y1 plus 1 equals to 2y2 will give us an odd number being an even number, which means that the conclusion will be false as well. So this disjunction will simplify to y1 equals to y2 or false or y1 equals to y2. Well, I think more precisely we can call this not just false, we can say it's a contradiction. We can use the letter C like this. But if you disjunction with a contradiction, you're just going to get whatever remains. And if whatever remains in this situation is a disjunction of the same thing, the conclusion is that you get the same thing. But that is precisely what we were aiming to prove at the beginning. And that's that. That is how we establish F2. And with all of that hard work, we have shown that F is a function. Takes a bit of energy, takes a bit of effort, but it can be done. We did it. Let's finish up this question before we go and prove that every integer is either even or odd, and not both. Let's look at the next question. In fact, let's clean up the board. I need the information here. I still need information here. Now we have this question. We are asking, is F surjective? Is F surjective? So that's our question. We need to check if F is surjective, which tells us that every output must have at least one input. I think we can try to visualize this with some pictures, and hopefully this can help us take a look at whether we get surjectivity or injectivity. So since we look at integers, we can consider the number line. It's a very useful visualization tool this way. Sometimes drawing useful pictures help make the proof make a lot more sense. So sometimes it's a matter of bashing the definitions like just now. Sometimes a picture helps. So here's 0, here's 1, here's 2, here's 3. I think we can do that. And let's consider these integers. So before we even try to figure out what's going on, before we try to answer the question on whether F is surjective, let's just see what is F. What is F doing, right? So these are all of the inputs and these are all of the outputs. And so n, y are connected if n equals to 2y or n equals to 2y plus 1. So we can think about it as either y equals to n over 2 or y equals to n minus 1 over 2. It's one or the other. So let's see what we get. Let's consider n equals to 0. If n equals to 0, then y is either equal to 0 over 2 or minus 1 over 2. But between these two options, this is the only integer. So we can connect 0 to 0 in this manner. For 1, if we plug in n equals to 1, then y is going to equal to a half, or y is equal to 0, because 1 minus 1 all divided by 2, that's 0 divided by 2, and that's 0. But this is the only integer, so we're going to connect 1 to 0. For 2, we're going to take 2 divided by 2 to get 1. And for 3, we're going to get 3 minus 1 all over 2 to get 1. And 4, by the same pattern, is going to go to 2. 6 is going to go to 3. 8 is going to go to 4. In fact, every even number is going to get thrown into the number, well, it's going to be thrown to the number after dividing it by 2. Like for example, 2, we divide by 2 to get 1. 4, we're going to divide by 2 to get 2. 6, we're going to divide by 2 to get 3. So on and so forth. And that might actually hint to us that, wait a minute, there are numbers pointing to 2 and 3. So we probably do get surjective, right? So claim f is surjective. Let's proceed to prove this claim. So we'll fix y inside the output space, inside these guys. We need to find some guy from the input space that gets mapped to y. And we've seen that any number, if you divide by 2, you're going to get the remaining answer. So let's choose the input to y. Since y is an integer, 2 times y is an integer as well. So n equals to 2y is in fact an integer. Then we have that n equals to 2y, right? So if n equals to 2y, that means that ny is an f. But that means, in terms of the function notation, that y equals to f of n, which is precisely what we mean by the function f being surjective. So that's that. We have, for any output, we have found an input such that the input points to the output. Therefore, f is surjective. Now, from this diagram, we also see that we have 2 inputs pointing to the same output, 0, and we can claim rather quickly that f is not injective. Here's a really short proof as well. Choose y equals to 0, right? There is an output that has 2 inputs, right? Y equals to 0, or rather choose x1, or rather n1 equals to 0, n2 equals to 1. Then it's pretty straightforward that 0 is not equals to 1. And yet, we do have a situation where f of n1, that's f of 0, that's 0, is also f of n2, that's f of 1. And therefore, we have violated the every output has at most 1 input rule. F is not injective. And there's that. There is one more question to this. This is actually our part C over here. There is one more question. And we can take a look at this next question before we move on to the our quick proof that every integer is either even or odd but not both. Now we've already seen that f is surjective. So that raises the question, what is the range of f? Now this is an interesting question because we've seen that f is surjective. So now what is its range? A lot of us are tempted to say that, well, the range is the codomain. That's not the case, right? The codomain is sort of the stipulated possible outputs within our context, but the range is really what the function actually produces, right? The codomain is just there, so we have A and B. The codomain is sort of just there as a setup to make sure whatever we're saying makes relative sense. However, if you consider all of the inputs, and you collect all of the outputs, the collection of the outputs is the range. So I like to think of B as the plausible outputs and the range as the outputs that is created by some input. So right away, we can see that the range of the function will always be a subset of the codomain. It is by definition a part of all of the plausible outputs. So that is the important part of a function. But now what is the range of f in our context? We know it's a subset of z. We've also, however, seen that f is surjective, right? We've seen that f is surjective, but what does that mean? It means that for any y in z, there exists some input x in z with the property that y equals to f of x. And what that tells us is that every output in z is created by some input in the input space. So it's not just a list of plausible outputs. Every plausible output turns out to be created by some input. But if it is created by some input, we can conclude that y must lie inside the range of f. But if any item in z is an item in the range of f, this whole thing helps us conclude that the range, or rather that z, is a subset of the range of f. So if we have these two features happening at the same time, we can only conclude one thing, that the range of f is in fact equal to the codomain. The range of f must be equal to the codomain by the definition of f being surjective. So here's a little exercise for you to try. I'm going to leave it here just for your consideration. So just let's establish, or rather as an exercise, you can try to establish some of the following results. It's the same results but more generalized. We let f be a function. 1. Show that the range of f lies inside the codomain of the function. And 2. Show that you get equality if f is surjective. In fact, it is a two-way. It's a two-way statement. You can prove that this will be true if and only if f is surjective. Okay, let me know your proof in the comment section below. Now let's take a short detour and prove a result which I claimed but I did not prove. I think some of us have seen this proof somewhere in some lectures before, but I'm going to prove it for the benefit of everyone else who is watching this leisurely. And here's the claim. Fix n in z, then n equals to 2k for some integer, or n equals to 2k for some integer k, or n equals to 2k plus 1 for some integer k, but not both. You can't have both at the same time. And the proof is pretty much the same as what we've seen just now, but let's prove it here, just for the lols, because why not? So we'll fix n in z, and we can try to establish a bunch of things. Well, either 2 is a factor of n or 2 is not a factor of n. So either 2 is a factor of n or 2 is not a factor of n. I mean, it's either one or the other, and you realize very quickly that if 2 is a factor of n, by definition, you can find some k in z with the property that n equals to 2k, and we're done. If 2 is not a factor of n, then you can do long division, right? You can do long division and obtain a remainder. So there exists a remainder r in z with the property that firstly n equals to 2k plus r. Secondly, this remainder has to be smaller than 2. Otherwise, we can just keep going. Now, I believe this is actually a corollary of a deeper result called the Euclidean algorithm. So I'm going to call this is due to the Euclidean . And if you want me to prove that, do let me know in the comment section below. So once that's the case, we can conclude that, well, if r is between 0 and 2, we have two situations. We have r equals to 0 or r equals to 1. If r equals to 1, we'll get n equals to 2k plus 1, which is what we wanted. If r equals to 0, then n equals to 2k, which means that 2 is a factor of n, which is a contradiction. So that is a situation here. We cannot have, n will be equal to 2 times k or 2k plus 1. We haven't shown that it can't be both. Let's do it really quickly. Suppose n equals to 2k for some k in integers, and well, suppose there exists some n in z with the property that n equals to 2 times k or n equals to 2 times l plus 1. We're not saying that the k in here has to be the same as the k in here. There's no guarantee. It's just a bit of a notational overload there. Suppose this is the situation. What do we have? We have a situation, therefore, that 2k equals to 2l plus 1, which tells us that 2 times k minus l equals to 1. And this tells us that, well, this tells us that k minus l is equal to a half. So on the one hand, the quantity on the left side is the difference of integers. So this is an integer. Or rather, we write it this way. This tells us that we have an integer equaling 1/2, which is not an integer. Right? It's not an integer. So we have a situation of an integer equaling a non-integer, which is a contradiction. It can't happen at the same time, and therefore we can conclude that this cannot be the case. You cannot have both happening at the same time, which is what we wanted to show in the first place. Just a quick digression into number theory over there. There are actually a few results which are quite interesting to show in this regard. But we'll look at that if time permits. let's look at the next question, which is a rather surprising question because it sort of violates our understanding of functions by introducing boolean functions. So I don't even know what's the number. I think it's 5 here. I jumbled up the order in the first 3, but afterwards I'm pretty much following the order of the questions. We're given, we want to define a boolean function in a particular manner. So we'll define the boolean function g like this by setting g of p naught, q naught, r naught to be the truth value that the compound expression, this is a mouthful, but let's just write it out here. P or Q implies negation of R evaluates to when one substitutes propositions. When one of truth values P naught, Q naught, and R naught. So this is a mouthful, but roughly speaking, we are defining G in this manner. Let me just rewrite that in a little bit more compact idea. So G of P naught, Q naught, R naught is going to be the true value obtained when you substitute P with P naught, Q with Q naught, R with R naught. So it's gonna be looking like this. And let's recall that if P naught and Q naught are propositions, they have their truth values, this whole thing is gonna have a true value. If this is a true value, this whole thing is gonna have a true value. This whole thing is gonna have a true value. This will either be true or false. It's gonna be one or the other. We don't know which, and we can't really be bothered. But roughly speaking, this long comment, if you would, is abbreviating to this equation, or rather this expression. This guy is gonna be a true or false. This will either take on true or false. So we're gonna cancel all of this and write this way. That's a lot cleaner. Where P naught, Q naught, R naught lie inside TF cube. And what TF cube basically means is triples, where each item can either be true or false, true or false, true or false. Just like before. So here's the question. Is G surjective? And secondly, another question, is G injective? Here's the question. Is G surjective and is G injective? Now, there are a few ways to go about it. In fact, the most direct approach would probably to fill up the truth table. Just do the truth table. It should work. Math people are really lazy, so let's just experiment with a few options and see how we can answer the question. So let's consider true, true, true. And when we substitute true, 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 we're gonna get true or true implies the negation of true. This will evaluate to true or true gives us true, implies the negation of true is gonna be false. But true implies false is gonna be false. That's gonna happen. It is what it is. We could also consider g of true, true, false, and I'm gonna avoid using colors because it's taking a lot of energy to keep swapping out the colors. So true, true, false. Is it gonna be true or true? Implies the negation of false, which is true implies true. We shall evaluate to true. And finally, we can also put g of tf. F equals to t or f, implying the negation of f, which is true implies false, which is true. You could go on, you could just write out all the different possibilities, but you will see very quickly that these three instances give us an enough justification of whether G is surjective or not. Well, G is surjective means every item in the output has at least one input. Could have more than one, we don't care, we just need to care about whether there is at least one input. And we can do that really quickly because for T inside the output space, we have there exists TTT in the input space, or rather TTF, pardon me, such that G of TTF is T, is true. And similarly for false, there exists TTT inside TF cube such that G of TTT is false. So for any output, we have found an input such that the input points to the output. Therefore, G is surjective. And fun fact, we have found two inputs that give us the same output. It's the same true. So we have found two inputs that give you an output. So that means G can't be injective, right? So we can justify it this way, right? So for T, 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 and well, TTF and TFF inside the triples, G of TTF is true, but G of TFF is also true. So you have found an input, you have found two inputs that give you the same output. Or rather, you have found an output that has two inputs. So G is not injective. Let's make some space. We're back to this question, and we've seen that G is surjective. We know that G is surjective, and G is not injective by our discussions earlier on. So here's a question. Give an example of a function f such that we can get G circle F is the identity on true F, or on true false, TF. So, well, what do we mean by the identity? The identity, I like to call it the do nothing function. So we'll define the identity on a set A by the function that takes A to A given by identity of x equals to x whenever x is A. I call it the do nothing function, it does nothing. So that raises the question, can we find a function f such that G circle F is the do nothing function? And do nothing in the sense that G circle F of true is true. G circle F of F is false. And here we see circles as well. Circles should ring a bell. This is actually the same circle, the composite relation expression that we've seen in the relations video. So we can write this actually. Turns out, by the way, that G circle F of t is actually equal to G of F of t and G of F of F. Right? If we were to run through the definitions of composition, we will get this. Do let me know in the comments if you want me to prove this, so we can do it as well. So we want G of F of t to be t, and G of F to be F. Now we've already seen a few inputs that give us true. In fact, we've seen that G of TTF gives us true. We've seen that G of TTT gives us false. So wouldn't it be great if we could set F of t to be TTF and F of F to be TTT? Why would we do that? Because if this is true, then if we apply G on both sides, G of TTF will give us true, which is precisely what we wanted to show. And likewise, if G of this guy is G of this guy, then G of true is going to be false, which is precisely what we wanted to show. Yeah, why not? Let's just define it that way. Yeah, let's just define F. Just define F by this. And we can check that F takes in true or false values. See, true or false. And it outputs a triple. It outputs a triple. Great. Now, it's not surjective. It doesn't hit every single triple, but it's still a function. Every input has at least one output. True has the output this guy. And every input has at most one output. Well, true has only this guy as the output. So it's still a function. F1 and F2 are satisfied. We still get a function that gives us the do nothing function. But this will raise a really curious question. When can we find these do nothing functions? Do nothing functions tend to have a lot of uses in math, so we might want to take a look at how to obtain such do nothing functions, which is precisely our next question. We'll let f be a function from a to b, and g be a function from b to a. We're gonna show something interesting. We're gonna suppose the following. F is surjective, and G circle F gives us the identity. In fact, if you make a comparison with the previous expression, or rather the previous question, you're going to see something a little bit familiar. So, suppose F is surjective and G circle F is the identity. What's our claim? We claim that G is injective. So if we know that G circle F is do nothing, we can immediately obtain that G must be injective. That's actually pretty crazy. So let's go ahead to prove it, and then we'll look at a few more questions. Now we want to show that G is injective, so we need to show that G is injective. So every output, or rather every output has at most one input, right? So we'll fix y1, y2 in B, and we'll suppose that G of y1 equals to g of y2. To show that g is injective, we need to show that these inputs are actually one and the same. So the first question is, how do we even start? Because clearly we can't do anything. Like, what are we supposed to have? There is a very sneaky result over here. And the fact is that y1 and y2 are inputs with respect to b, and yet they are outputs with respect to f. Right, so y1 and y2 lies in b. From g's perspective, y1 and y2 are inputs. But from f's perspective, y1 and y2 are outputs. And we know that f is surjective, right? So if f is surjective, every output has at least one input. So since f is surjective, the output y1 has an input x1, and the output y2 has an input x2. And the inputs both lie in A with respect to the function f. So we have y1 has the input x1 and y2 has the input x2. That's rather remarkable. That's kind of surprising over there. What does that communicate to us? Okay, so how do we continue from here? Well, now we have y1 in terms of f. That's great, because now we can try to maybe use this guy to our advantage, right? We really use this. We can try to hopefully use this. That might be helpful. So we can now use this information to obtain that g of y1, because that's g of y1, is equal to g of y2. And because we have g of f of something, we can write this as g circle f of x1, and we can write this as g circle f of x2. But we do know that g circle f is the do nothing function, right? It's actually the do nothing function on A. x1 lies in A, so there's no problem there. So the g circle f of x1 must be x1. And g circle f of x2 must be x2 by the similar train of thought. So we can summarize our findings by saying x1 equals to x2. But that's not our goal. Our goal is y1 and y2, and here's x1 and x2. We want to ask, how do these things connect? Well, here we have y1 equals to f of x1 and y2 equals f of x2. So here's the question. If x1 equals x2, is it true that f of x1 and f of x2 are equal to each other? Because you have the same input, you must have the same output, because f is a function. So that equals to each other, which means that y1 equals to y2. And that is how we obtain the goal. Conclusion, G must be injective. So really sneaky trick over here. We have a few more results later on which we can try to show as well. There are some interesting ideas in this question set and in the next question set. So stay tuned for that. But for now, we're gonna look at a induction question, which is a really sneaky induction question. If you've never seen this before, you probably wouldn't even know what's the problem, right? So here's a very bold claim by a student in the National University of Singapore. Now, of course, there is a more famous result. I think it's called the all horses are of the same color. But let's just contextualize it to the university that I graduated from. So, claim. Okay, and I'm gonna put quotes there because it's actually not exactly correct. And here's the sentence. Let Pn be the sentence that if NUS has N people, then all these people have the same birthday. So he's gonna try to prove this by induction. Okay, let's see how far he goes. Let's call this the proof. The base case is if we have, say, one person. So we're gonna define this to be over the positive integers here. So let's try one person and see what happens over there. So for one person, we get P of 1. Right, we get P of 1. So suppose NU has one person, then it has the same birthday as, he has the same birthday as himself, he or herself, right? So then this person has the same birthday as, I mean, I could use he, himself, herself. I'm just gonna use gender neutral here not because of, you know, any agenda, it's just I'm lazy to distinguish. I'm just gonna use this because I'm too lazy to make the distinguishing factors. So therefore, P1 is true. Oh, great. Okay, then what? Okay, so now here's our induction hypothesis. We'll suppose that Pk is true for some k in natural numbers. So let's now suppose that NUS has k plus 1 persons. And we can write them out as P1, P2, Pk, and Pk plus 1. So let's call this group here S. And we'll say, and we know that S has k minus 1 people. So let's observe that S union P1 and S union Pk plus 1 are sets containing are sets of size n, right? So all of these guys have n persons. By the induction hypothesis, people in S have same birthday as P1. That's from the first collection of k people. And likewise, by the same logic, they must have the same birthday as the person Pk plus 1. It has to be the same. So therefore, they all have the same birthday. And you might be wondering to yourself, wait, what happened here? What's going on? Why is this suspiciously true? You might be wondering to yourself, wait a minute, what happened here? What's the bug? Why did that happen? That shouldn't be happening, right? That shouldn't be happening. Well, here's the question. We suppose that this is true for some k, but is it true for k equals to 2? Is it true? Is it true that k equals to 2? Right? So, the problem over here is that in the case when s equals to 1, right, do we allow s to be non-empty? I think we don't allow s to be non-empty, right? So let's look at the k equals to 2 situation. Suppose NUS has 2 persons. You can easily find 2 people with different birthdays, which means that P1 is true does not imply that P2 is true. But wait a minute, doesn't the induction argument work? Well, the assumption here is that if S is empty, then yes, then people in S have the same birthday as P1. But if it is non-empty, all bets are off. All bets are off. So the key trick here is that we assume that this guy is non-empty. However, in the k equals to 2 situation, this guy is actually empty. S is empty. Right? So the problem is over here is that if, in fact over here, if S is empty, then yes, people in S have the same birthday as P1 vacuously. And people in S have the same birthday as people in S2, as the same birthday as people in the other set vacuously. But doesn't mean that P1 is the same birthday as P2. And that's the bug. Then yeah, I mean, then people in S have same birthday as P1. And similarly, people in S have the same birthday as P2. But because S is empty, but if S is non-empty, all bets are off. So that's a really subtle argument over there. We assume that S was non-empty. And that's what happened. So clearly, the proof is the claim doesn't work. But it's a really sneaky proof, right? Wow, that might have evaded us if we keep thinking in terms of a direct induction formulaic type of proof. So that's that. Alright. We're gonna take a short break and then we're gonna finish up the questions over here. And we have a few more questions in the extra exercises. So stay tuned for that. Alright, let's look at the question. The next question. We have a few extra exercises on functions. Let's take a look at those and then we'll call it a day. So we're going to define f to be the relation on the rational numbers. And we're going to define g as also a relation on the rational numbers. And we want to ask the question, is f a function? And is g a function? Those are the two questions. And with these questions in mind, well, we need to think about how to go about it. Well, perhaps a few pictures might be useful for us. Since we're working with rational numbers, the 2D plane is actually pretty useful to visualize rational numbers. in this situation, we have y can either be plus or minus x. So we're going to get y equals to plus x. This will be the picture. Y equals to minus x, we'll get this picture. And y equals to, well, y times x squared plus 1 equals to 1. We're going to get the expression, whoops, y equals to 1 over x squared plus 1. This is actually a legitimate expression because the denominator would never be 0. It's always not smaller than 1, and 1 is strictly positive. And it's hard to draw this picture, but we can think of it as x squared plus 1 gets larger and larger and larger, y will approach 0 because 1 over something big will go to something small. So it's going to look a little bit like this. And then in the other direction, x squared plus 1 will also blow up. So we can sort of go down like this as well. The particular picture is not as important as the intuition. And so is f a function? Probably not, because we can already see that for this particular input, we're going to get 2 outputs. So it's pretty unlikely. And firstly, for f is not a function because we have 1, 1 is inside f and 1 minus 1 is inside f. Alright, you have x, you have y equals to x in there, and you have y equals to negative x in there. So both are there. Therefore, f1 is violated. And g, based on our picture, looks a lot like it's gonna work. So g is a function. That's our claim. So let's prove the claim. Now to show that g is a function, we need to show that every input has exactly 1 output. So you can prove at least 1 output and at most 1 output. But let's just see what we get. We'll fix x inside the rational numbers. Then 1 over x squared plus 1 is a unique rational number. Let's put it this way. 1 over x squared plus 1 is unique. There's only one number such that 1 over x squared. There's only one number, or rather, if you have a fixed x, then 1 over x squared plus 1 is exactly one number, right? So let's check. Then y, define y, we can define y this way, equals to 1 over x squared plus 1. This will be unique. Then y x squared plus 1 equals to 1, which implies that xy is in G uniquely. The key idea here is that if x is a fixed unique number, then 1 over x squared plus 1 must be a fixed unique rational number. We can justify it a little bit more carefully because x squared plus 1 is rational and x squared plus 1 is bigger than or equals to 1, which is bigger than 0. This would give us that 1 over a rational number, 1 over a positive rational number is still a rational number. And we get that a unique expression. So this sort of helps us solve f1 and f2 at the same time, right? The fact that this is a situation is f1 and the uniqueness is f2. So this is a valid proof. Way shorter, definitely not as long, can be done. We're allowed to do it that way. We're going to define something a bit interesting, so we'll let f a b be a function, and we're going to suppose that the relation f inverse is a function from B to A. We claim, therefore, that f is a bijection. Now, I don't think we've ever really encountered bijections so far, but just a recap of what bijections are. A bijection is, well, let's just write the definition here. The function is a bijection precisely when it is an injection and it is a surjection. So that's what we need to establish. We need to establish that f is both an injection as well as a surjection. We know that f is a function, so we just need to show that f is injective and f is surjective. So here's our claim, here's our proof. We need to show that f is injective and f is surjective. So let's first show the first goal, which is that f is injective. So how do we prove this goal? We'll fix outputs. So injective means that every input or every output has at most one input, right? So we'll fix x1, x2 in A. We'll suppose that f of x1 equals to f of x2. Our goal is to show that x1 must equal to x2. And once again, it feels like we can't really do a lot over here until we realize something very important about the question. The question here never assumes that f inverse is a function. Well, it does, but the key trick is to take a look at this guy, the relation f inverse. If we just write it this way, it's not entirely obvious how we should go about it. So here, I'm actually gonna fix y in B such that we have this property. We might actually want to write this using relation notation, because inverse relations, we only know inverse relations through relations. We know nothing about inverses through functions right away. So let's go with that. So if y equals to f of x1, this tells us that y, or rather x and y, lies inside the relation f. And if y equals to f of x2, then that tells us that, well, x1, I mean, and then that tells us that f of x2y lies inside f as a relation, not as a function, as a relation. But if x1y lies in the relation, then yx1 lies inside the inverse relation. The inverse relation is all of the flipped pairs, all the pairs that get flipped. And instead of x2y being in f, we're gonna get yx2 being in f inverse. So now we have a situation where yx1 is in f inverse and yx2 is in f inverse as well. Y in this context is the input, x1 and x2 are the outputs. So the input y is going to give us the output x1 as well as the output x2. But f inverse, by our supposition, is a function. If f inverse is a function, every input has at most one output, which means that if x1 and x2 are both outputs, we must get x1 equals to x2. And we've met our goal, and we have shown that f is indeed injective. Let's clear the board and conclude that f must be surjective as well. We've already shown that f is injective, so now let's go ahead to show that f is surjective as well. So here's our goal. Well, what's our goal actually? our goal is to show that f is surjective, but what does it mean to have f being surjective? It's to show that for any output, there exists some input that gives that output. So how do we go about this? Well, let's fix y in B, and our goal is to show that there exists some x in A with the property that y equals to f of x. And at this point in time, it's like, wait a minute, what exactly is? How do I even find it? I don't even know what's A. I thought to prove a existence proof, I need to create the number, but I don't even know what A is. It's so abstract. I can't do any of this. One of my rules is thou shalt not panic. So one step at a time. We can write y equals f of x as, again, taking our cues from the previous part, x comma y in f. We'll treat f as a relation because functions are relations, that's fine. And we can immediately talk about the inverse relation. So we need to find an x in A such that yx is in f inverse. But f inverse is a function. F inverse is a function. So since f inverse is a function, every input has an output. In fact, the input here is y, correct? So every input has an output, has at least one output. So there exists some output with the property that yx is in f inverse. But we've seen that if yx is in f inverse, by this train of thought, this expression is the same thing as saying that y equals to f of x. And then we're done. Because every output with respect to f has an input, x in A. So the idea here is almost that f inverse is literally going to do the exact opposite of f, right? Inputs in f are outputs in f inverse. Outputs in f are inputs in f inverse. And so that's the sort of the key insight that helps us check that f is injective and surjective. Oops. Which concludes for us that f must be bijective. And that's that. It's a rather cute little result there. Now we are going to go back to a relation that's kind of annoying. It's kind of annoying. So we have f as defined as before. We're going to define f as n. I'm going to use y, even though the given question uses the letter x, but I'm just going to use y because it makes life easier. Right? Inside the integers with the property that n equals to 2y or n equals to 2y plus 1. We're now given a new function g in the form xn in z squared with the property that n equals to 2x. So it's a slightly different function. Now the x's and the n's have swapped, right? So there's a little subtle difference over there. And we can go ahead to ask the question. Well, in fact, the claim is that g is a function from z to z. That's our claim. And so, I think the proof is actually really similar to one of our previous questions, because if we were to fix x in z squared, then 2x as an integer is unique. There's only one integer such that is equal to 2x. So define n equals to 2x uniquely, which means that nx is in G uniquely. Once again, this establishes F1 because you can find an n such that nx is in G. Well, xn is in G, apologies. And you can find you can show that this is unique because of F2. You can break down the proof if you wish, but I think this is a fair argument over here. So we do have that G is indeed a function, and we can ask the question, is G surjective? Is G surjective? So once again, I think a useful way to represent functions from integers to integers, you could either use a xy plane, or you could use these useful arrows. So here's z. Here's 0, 1, 2, 3. Here is 0, 1, 2, 3. Let's go to 4. And let's just see what happens. Well, when x is 0, and here x is gonna be the inputs, n will be the outputs. If x is 0, then n is gonna be 2 times 0, so that's 0. If x is 1, then n is going to be 2 times 1. If x is 2, then n is gonna be 2 times 2, so that's 4, and so on and so forth. It's just gonna get higher and higher. So it's kind of pretty, it sort of identifies for us that 1 cannot be mapped to, right? And therefore G cannot be surjective. So the answer, no, because 1 is not even. Right, so therefore, for n equals to 1 as an integer, for any x in the input space, n cannot be equal to 2x because n is 1, it's not an even number. So it's definitely not surjective. But is it injective? Is it injective? The picture sort of shows us that we're probably going to get injections because it's all sort of spreading out. So let's see if we can prove this in one line. So my claim is that this guy is injective, but we need to prove it. We'll fix 2 items in the input space. That tells us that, well, we will suppose that g of x1 equals to g of x2. But that tells me that g of x1 is going to be n, which is going to be 2 times of x1. This will equal to 2 times of x2. And this combines to give us x1 equals to x2. So if the outputs are the same, the inputs are the same, we can conclude that x1 equals to x2, and we do get g being injective. So that is true for our purposes. And we have a very sneaky result coming up in just a moment. Now, we have a claim. Here's our claim. F circle G is the do-nothing function. Is the identity on the integers. But if you were to flip it around, you no longer get identity. You no longer get identity, which is kind of surprising. It's like, wait a minute, huh? What's going on here? So let's prove it. To show that it's identity, we need to fix x inside z, and we need to show, our goal is to show that f circle g of x is going to be equal to x. That's what it means for f circle g to be the identity. But f circle g of x can be opened up to be f of g of x. So let's see what we get. So g of x is by definition 2 times of x. And therefore g of x is an even number, right? But f of that is f of 2x. It will divide by 2 if it's even, or subtract by 1 and then divide by 2 if it is odd. In this case, 2x is even, so we're going to take 2x and divide it by 2. And we're going to get x. So let's just really quickly establish that. So f of 2k is equal to... well, what's f of 2k? Let's suppose, let's do it this way. We will suppose n 2k is in f. We want to show that n will be equal to... oh, give me a... oh my gosh, this is not hooking up. Suppose 2k, y is in f. My claim is that y must equal to k. So it's a really quick proof here. So this tells us that either y... well, this is awkward. 2k equals to y, or 2k equals to 2y plus 1. But this will give us an even number equaling an odd number. Contradiction. I think I did this wrongly. This is kind of awkward. Sorry, 2k equals to 2y. Either 2k equals to 2y or 2k equals to 2y plus 1. But the second option gives us a contradiction, which means that y must be equal to k. And there's that. However, so we've already shown this guy. We've already shown that f circle g is the do nothing function. However, g circle f is not the identity function. So that's kind of irritating. So how do we show that g circle f is not the identity? Well, let's just consider an example. Let's use the odd number example. That's probably gonna mess us over. I've got a gut feeling that's the case. So we'll choose x equals to 1. Then let's consider g circle f of 1. G circle f of 1 is g of f of 1. Right? And f of 1 is going to either divide by 2 if it's even, or subtract by 1 and divide by 2 if it's odd. In this case, 1 is odd, so we're going to subtract... In this case, 1 is odd, so we'll subtract by 1, that gives us 0. 0 over 2 is 0. So f of 1, in fact we've seen just now actually, right? F of 1 is actually equal to 0. So this will give us g of 0. And g is going to be 2 times of the input. So it's 2 times of 0, which is 0. But 0 is in the integers not equals to 1. So therefore, g circle f of 1 is not equals to 1. And since we found one item that violates the do nothing condition, g circle f cannot be the identity on z. It's not possible. Doesn't work. And we have one last question. So we've already proven this guy. Let's clean up the screen and establish that. Let's clean up the screen and establish our answer. I don't think we need to clean the screen, I just realized. It's a really quick question. So here's a final question for the day. Is G equals to F inverse? And I think we can see that the answer is no. The problem is that we've seen, or at least we can show, roughly speaking, that F itself is not even injective. And if F is not injective, F inverse doesn't exist as a function. As a relation, it surely does exist, but not as a function. So G is a function, F inverse is not a function. So the answer, no. Because G is a function, but F inverse is not a function because F is not injective. And we've proved it before that F is not injective. You can go check out the full stream or the short form video that is out, or a various bunch of sources that help us establish that F cannot be injective and therefore F inverse cannot be a function at all. And that is it for functions. It involves fundamentally the ideas of every input having at least one output, every input having at most one output, every output having at least one input, and every output having at most one input. The first two establish functions. The third condition is surjectivity. The fourth condition is injectivity. And the second two conditions establish bijectivity, which gets us inverse functions. And of course, we have the famous do-nothing function as well. In fact, we use the do-nothing function in a sense to define the bijection, or at least to describe the bijection in a convenient manner. So that's that for functions. We can use functions to talk about sizes of sets in a relatively abstract sense. That might take a bit of effort in the next topic on cardinality. So stay tuned for that, and I'll catch you guys in the next one.